Okay, so this is section 9.3. We're going to talk about circular motion here, and this is a little more practical than, or something that might be a little more practical as far as something you've seen in your everyday life. So, circular motion. So let's say, remember Newton's second law, force equals mass times acceleration. So if we're moving an object and it's moving at a constant speed, it'll keep going in that constant speed until something else acts on it. That's the law of inertia. An object's going to continue to go in a straight line until another force acts on it. Well, what happens if we make that object move in a circle? So let's say it's moving in a circle with a constant speed. We have to apply a force to get it moving in that circle, and that force is going to be directed towards the center of the circle and acts on that particular object. So if we have a string attached to this ball and we're whirling it over our head, the force applied to the string is going to act towards the center of that circular path that this object is making, okay, and vice versa, okay? So swinging in a circle overhead requires an inward force. In the figure below, the tension in the string provides that force. So this thing, as long as you're applying that same tension in that string, that ball is going to keep circling over your head, over your head, over your head. But if the tension in the string changes, then the path is going to change. The ball will fall, it'll go off in a straight line, it will change. It will not continue in the same path with the same speed. All right. So the force acting on the ball is always perpendicular to the ball's motion. Therefore, it changes the direction of the ball, but it doesn't change the speed. So that force, that tension in that string is going to keep pulling that ball in that circular path. So it changes its direction. Oops. So we change the direction of the ball because of the string, but it doesn't change the speed of the ball. Since the ball is acting on by a force, it's directed toward the center of the circle, then the ball is accelerating towards the center of that circle. The acceleration that results from this center-directed force, I don't know why that won't underline, is referred to as centripetal. Well, that's weird. Is referred to as centripetal acceleration. Oh, somehow I've moved my slide. There we go. So that is centripetal acceleration, where the CP stands for centripetal. Centripetal just means, just like if you broke the name down, it's a center-directed acceleration and a center-directed force, okay? So think about your own personal experience. If you're driving in a car and your car goes around a curve really, really fast, you will feel pushed to one side or the other. The tighter the curve, the greater that centripetal acceleration, and the greater the force with which you are pushed to one side or the other, okay? So the magnitude of an object's centripetal acceleration depends on both the speed of the object and the radius of the circle. So how tight the circle is, as well as how fast that object is going around. So the equation is actually, so centripetal acceleration is actually the speed squared divided by the radius. Speed squared divided by radius. So there is our equation. Make sure you have that memorized and you know what each of those things stand for. So ACP is a centripetal acceleration, V is your linear velocity, and R is your radius, okay? Newton's second law states that force equals mass times acceleration. So the force that causes this circular motion is called centripetal force, and it is mass times centripetal acceleration. So centripetal force, FCP, is going to equal to mass M times V squared over R. Okay, and that's going to come up on the next screen. All right, so you see there's your equation. So during circular motion, centripetal force has a constant magnitude, v squared, mv squared over r, is always directed toward the center of the circle. And it is always perpendicular to the tangential velocity of the object in circular motion. So the linear velocity, okay, in circular motion. Okay, so here's your object going around in a circle. Okay, your centripetal force is going to be acting perpendicular to the tangential velocity. It's always directed towards the center of the circle, and so is acceleration directed towards the center of the circle. Okay. So, some other practical things you may have experienced in having centripetal force and acceleration. Explain those things. You can experience the effects of circular motion when riding in a car. So perhaps you've noticed that you feel heavier when the car you are riding in encounters a dip in the road. This change in apparent weight is due to the approximately circular motion of the car. As you go through the dip, the normal force acting on the car and on you has to increase to supply that centripetal force. Okay, so if you've ever been going down the road and all of a sudden there's this big dip in the road and you just feel like your stomach drops kind of feeling, that's what's going on. It feels like there's a change in your weight due to the motion of the car. So here's another practical application. When you skid on a car, so if you ever, hopefully you won't, hydroplane, or if you're ever on ice and you start sliding, they always tell you to turn the car in the direction of the skid. So if you start to skid to the right, you're supposed to turn your wheel to the right. Skid to the left, turn your wheel to the left. And this seems counterintuitive, but it works because of centripetal force and centripetal acceleration. It works because increasing the turning radius and decreases the centripetal acceleration, so it'll slow you down. This in turn will decrease your tendency to skid, and you'll come out of that skid. But so it seems like, well, why wouldn't you just keep trying to go straight, or why wouldn't you correct by going in the opposite direction? You don't. You actually correct by going in the same direction that the car is skidding, and that is because of centripetal acceleration. You're increasing the turning radius, decreases the centripetal acceleration, and decreases your tendency to skid. Okay, so little practical knowledge there brought to you by physics. Okay, so the other practical application, well, it's not an application, as an explanation, I guess, is the tides. For years and years and years, the ocean tides and what causes the ocean tides and when they're going to happen and all of that. Well, not when, but what causes them is a mystery. But when we learned more about the circular path and about centripetal acceleration and centripetal force, we were able to understand low and high tides a little bit better. Force is required to cause an object to move in a circular path. So you have to have a force applied in order to get that object to go in that circular path. And that force of gravity becomes weaker with the distance. So the further away, force of gravity becomes weaker and weaker. So the drawing on here, so this drawing right here, shows the that the force exerted on various objects has different magnitudes. So the size, you can see the size of the arrow. And notice that the further you get away, the smaller that arrow is, or the smaller that force is. Okay. All right. So let's move to the next slide. And we'll probably come back and forth between the two. Comparing the force at the center, the right, and the left, you see that the object's near, that the near side of the object is pulled closer to the center of the mass, and the far side of the object tends to be farther away from the center of mass. So let's go back. So you can see that here's your object. This side is closer. So this side of the object is closer to the other object's center of mass compared to this side. So when this side is going to feel a stronger attraction than this side is. Oops. This causes the shape of the object to be deformed and form more of an egg shape than a perfect circle. So the drawing on the right shows how the water on the Earth's ocean gets deformed into that egg shape. And again, it gets deformed because the side that's closest to the sun is going to feel more of a gravitational pull than the side that's further away. And so it's going to deform into that egg shape. And since water in the oceans can flow, when the ocean deforms, that water is going to flow and it's going to become more, it's going to have more of a deformity than just a rocky surface on the Earth. So the Earth bulges on its sides too, but the amount that deformation, how that deformation can change, depending on where it is relative to the sun, it's a little harder for a solid object to change that. But water, liquid, it can be deformed and compressed a lot more than a solid. So those oceans are going to get deformed and have a greater effect than the solid will. And so that's going to result in those tidal bulges. So in one part of the Earth, we go back. So during high tide, this side that's closer to the sun, if this is orbiting the sun, this side is closer to the sun. So this whole thing is going to squish in, okay? And that water is going to bulge out on either side. But then as you go around and you continue to move, then that's going to change. That's why high tide and low tide come at different times in different places. Not everybody has high tide at the same time. Because again, you're rotating around, moving in that circular motion. So those bulges are going to move from place to place on the Earth. And it's not based on, never mind. I might say something I don't really know. So I'm going to move on. And we already talked about that. And that's planetary motion, which is 9.4, which we will talk about next time.